Hello. So today we're going to discuss functions and their graphs. So let me briefly review the learning objectives. So first we define what is a function, how to find its range, domain, etc. Then we discuss graphs of functions and the vertical line test, piecewise-defined functions, in particular absolute value function. What does it mean for function to be decreasing and increasing, even and odd functions? Okay, so what is a function? So here's the definition from Thomas Kalkos. So a function f from a set D to a set Y is a rule that assigns a unique value f of x in Y to each x in D. So basically it's a rule. So let me show the picture. So you have a set D and you have a set Y, right? So set means we have elements in it, right? In both sets, we have some number of elements. And this is a rule, so it assigns. So to each value in D, let's say a point X, it maps or it uh, assigns some value, some element Y, right? So that's my f. And what is important for this function, that this it, it needs to be a unique value in here. Okay, unique value. So in particular, uh, one point from D cannot go to two different points. It can't go to two different points. So this is not allowed. Okay. However, the following situation is perfectly fine. You may have a situation where two different points in D can be mapped, can go to the same point. So this is perfectly fine. This is fine. Okay. So how you sort of remember it? Well, you can think of this as a mothers and children, right? So one mother can have two children. So you can think D to be the children, right? Set of children, and this is Y is set of mothers, right? So one mother can have more than one child. However, one child cannot have two different mothers, right? So this is how you can sort of remember. Right. What is D? So D is called this the set that you see on the left is called the domain. Okay, and on the right Y, uh, we call it codomain. So it can be it's called codomain. Codomain. However, there's also a notion of range. So what is a range? So range, uh, this is the set of all possible values. Possible values. Values f of x, right? So here in this case, we write y is equal to, so y is equal to f of x. Okay, it's pronounced like f of x. So range is set of all possible values in. So basically, what can happen is your function may be mapping the points in your domain into smaller set, right? It might be mapping into smaller set, and there might be some points outside. So this mapping point, this is what we call the range of a function. So let's do some examples, how to find the domain and the range examples of functions. Okay, for example, I can take f of x is equal to x plus 2, right? So let's do one example. So what is it? Uh, so what are the possible values that x can have here? Well, I think x can be any number in reals, right? So this is bold R is stands for real numbers. And what could be your range? So here it's all R, so it means the domain of the function f is all of R, right? It's all of R. Or if you wish, you can also write like minus infinity to infinity, right? How about the range, right? How about the range? So what are the possible values? So if your x runs from minus infinity to infinite, what happens to x plus 2? Well, it will also run from minus infinity to infinite, right? So it means the range of f is also minus infinite to infinite. Well, okay, so let's do a slightly different example. For example, I can consider, let's do g of x, a function where we get 1 over x, right? So clearly x cannot be 0, right? So x cannot be 0, but other than that, it's fine. So which means its domain uh, can be written as minus infinite to 0, but 0 is not included, and set union from 0 to infinite, right? And then you think, if you vary your x within these allowed intervals within the domain, what happens to 1 over x? For example, when x is very large, 1 over x is very tiny. However, when x goes to 0, it becomes large number 1 over x, right? And similarly, if x is negative, then 1 over x is also negative, etc. So it looks like it will cover uh, almost all possible values. However, it cannot cover, for example, 0, right? Because for this quantity 1 over x to be 0, you need to have x equal to infinity or minus infinity, but infinity minus infinity are not numbers, so we cannot assign it. So basically this means range here, range is also from minus infinite to 0, but 0 is not included, from 0 to infinite. Let me do one more example. Let's consider, for example, h of x equal to square root of x. Okay, so what could be my x? We know that inside of square root we cannot have allow negative values, so which means my x must be non-negative. So that's the domain, right? So it's usually easy to find domain, which we also call it natural domain when we consider all largest possible values, so natural domain. So what is the domain in this case? It's 0. 0 is fine. 0 is 0, so we can include 0. That's why there is a square bracket. So that's my domain. How about the range? Well, again, square root cannot be negative, right? So it takes all it may take all non-negative values, and indeed if x is ranges between 0 and infinity, you can see that square root of x will range from 0 to infinity. So range is also 0 to infinite. So we'll see more examples as we go along. So let me continue with the next objective, uh, namely graph of functions. So what is a graph of function? It's looking at the function in the xy plane. That's the Cartesian coordinates, right? So basically graph, if you have a function y is equal to f of x, then by the graph, we mean all the couples x comma f of x, right? Such that where x ranges in its domain, right? In its domain. So that's the graph of a function. Well, let's do an example. Let's take f of x is equal to x squared. So what is x squared? We know from high school, it's a parabola, right? So let's try to kind of sketch it. Basically, let's first try to find the domain. So what is domain? So what are the natural domain, right? So what are the allowed numbers in x squared? Uh, so there are no division by zero, etc., etc. So we see that any x, we can assign any x here, right? So this means my domain here is all of R, all of R. Okay, how about the range? How about the range? Well, x squared can only take non-negative values. And if you range in R, right, if you vary from minus infinite to infinite, pick any number, etc., etc., and if you square it, it always becomes positive, unless it's zero. If it's zero, then it's zero. So the range is from zero to infinite, right? So zero is included. Uh, right. Now, how do you sketch? So you can come up with, because I need to plot x and f of x on the xy coordinates. So let me sketch my xy. Here's my x axis. Here's my y axis, etc. So I need to come up with a table of values, right? So here I need to have my x. Here I need to have my f of x. I need to plot this one. So for example, I can start with 0. If x is 0, then f of x is x squared, remember? So 0 squared is 0. If I let x equal to minus 1, then minus 1 squared is 1. If I let x equal to 1, then 1 squared is 1. If I let here is, let's say, minus 2, here I get minus 2 squared is 4. If I let 2, then it's 4, etc., right? So let's plot these 5 points. So zero is right here. Let's do like 1, 2, 1, 2, 3, 4, minus 1, minus 2. So when it's 1 and minus 1 is 1. So here's 1, 1. Here's a minus 1 and 1. Here's my 2, right? This is my 1, this is 2. So when it's 2, I need to, my y coordinate is 4. So this is my 4. Here it is, right? And when it's negative 2, it's 4 again, etc. So let's join these 4 points. That will give me roughly the graph of this function. Sorry, it was supposed to pass from this. Well, if you want to be very accurate, you have to plot more points, right? You have to find the tables of more points, and then you will get much accurate values. Now that we know the meaning of graph, we can discuss the next objective. So our next objective is vertical line test. So you remember this uniqueness, the domain we can think of as the set of children, the range or codomain we think of as the set of mothers, right? So what is a vertical line test? So vertical line test says the following. Uh, for a function, so here, for, let's say, for a assignment, for a relation, for a rule, you can say for a rule or for a relation, for a rule to be a function, to be an honest function, uh, every vertical line has to intersect the graph at most once. Okay, so this at most is related to the uniqueness. So what I'm saying is the following. You may have some sort of a graph, right? And if you want to find out whether this is really a graph of a function, whether it's coming from graph function, you can try to uh, look at the vertical lines, right? All these vertical lines. So for example, here, it intersects at most once. Here, it intersects once. Here, it doesn't intersect, right? No intersection, sorry. Here is no intersection, etc., right? So at most once. So yes, indeed, from looking at the graph, we can say, yes, this is a function. So this is a function, okay? Let me give a non-example. So for example, let's look at the circle. Some sort of a circle, not this metric. So here. Now, if you look at apply this vertical line there. So for example, here, okay, it doesn't intersect. So that's fine, right? However, when I sketch vertical line here, it intersects twice, right? So this means this is not a graph of a function. Yes, we can represent it with equations, but we cannot say that this is a graph of function. It's not a graph of function. Okay, so vertical line test. That's the vertical line test. So our next objective is piecewise defined functions. So sometimes it may not be easy to represent a function in sort of one line. So in this situation, you may want to define it in cases, right? So things like if the function, if x is negative, then it takes these values. If x is positive, it takes that value, and so on and so forth. Okay. So a nice example is, in fact, the nice example it comes from absolute value function. So, and a very important function in fact, absolute value function. So what is absolute value function? We all know it. F of x is equal to absolute value of x, modulus x, right? You may also know its graph. So graph looks like this. Here's the graph. So we sometimes write y is equal to x, right? This is y equal to whatever. So this is the graph. But how can you represent, if you don't want to represent it by this modulus symbol, right? How you can represent it is differently. Well, here it is. I can say that if x is positive, then absolute value of x is what? It's simply x, right? If x is negative, then absolute value of x is, because x is negative, I need to multiply by minus, right? So it becomes minus x. What happens if it's 0? Well, you can say that it's 0 if x is 0, right? If you like. So here, this is example of a case-defined function. Okay? This is an example of a case-defined function. Okay, increasing and decreasing functions. So what does it mean for a function to be increasing and decreasing? Well, here's the definition again from Thomas' book. So let's say that my function is defined on some interval, right? Maybe not on the whole of R, but in some interval. It's not important. So we say that whenever x1 is less than x2, if f of x2 is bigger than f of x1, then it's increasing, right? So let's visualize. So my x1 is right here, right? Somewhere here. My x2 is bigger, right? Here it's larger. And my f of x1, so here's my f of x1, right? This might be my f of x1 here. It's smaller, so which means x2 is, f of x2 is higher somewhere here, right? F of x2, right? So that's the example of increasing, right? So you see, if we go from smaller values to larger values in x-axis, my y-axis also increases, right? So it's increasing function, right? And decreasing is, well, again, if x1 is bigger less than x2, then it's the opposite. So f of x2 is now smaller. So this is increasing example. So increasing. Let me give an example of a decreasing graph of an example of decreasing function. So it's something like this, right? So it decreases, it goes down, right? So here's my x1, here's my x2, etc. And if you compare the values, uh, we see that this is my f of x1. It's bigger than f of x2, right? F of x1 is bigger than f of x2. So that's an example of graphs for decreasing functions. Decreasing. So basically, you need to check, and this needs to be true for every such x1, x2. Okay, it's not just for two x1, x2. You have to check it for every single x1, x2. So whenever x1 is less than x2, you need to have f of x2 is bigger than f of x1. Then we say it increasing. Otherwise, we call it if f of x2 is less than x1, f of x1 always. Then we call it decreasing. Okay. Now let's discuss another kind of functions. We call it even or odd functions. So here's the definition, again from Tom's book. So given the function y is equal to f of x, a function is said to be even function if f of minus x is equal to f of x. An odd function is f of minus x is minus f of x. Okay? So let me give a example for the even. So here's example. Take, for example, f of x is equal to x squared, parabola. Then let's check if this condition, this f of minus x is equal to f of x. Well, let's start from f of minus x. What is f of minus x? Well, it's minus x squared, but this is minus x times minus minus will cancel, so it becomes x squared. Well, what is f of x squared? Well, this is just f of x, right? So you see, I managed to show that this f of minus x is equal to x. This is true for all x, right? For all x in the domain. And here, if you remember, the domain was all of R. So this means this is showing that this f of x, well, f of x squared is even function. Okay. How about an odd function? Well, let's look at the cubic polynomial, simply x cubed. Now let's start again from f of minus x for arbitrary x, right? So what is this? This is minus x cube. So because minus 1 to the power 3 is minus 1, so this is minus x cube. But this is simply minus f of x, and this is true for all x. So this means my my function is odd. Bear in mind, there are functions that are neither odd nor even. Okay, so you cannot simply classify functions into two categories, like even odd. There may be functions cases where none of them is true.